Before we proceed with the analysis, let's take a quick stock. Remember, we're starting with the Poisson probabilities P of k, or more elaborately, P of k with a fixed parameter lambda. K runs over all the non-negative integers. We've discovered the basic Poisson identity for k times P of k, and we milked this to get another identity for k squared times P of k. We'll put both of these to good use shortly. But now let's come back to our problem at hand and imagine a chance experiment which produces an integer value x according to a Poisson distribution with parameter lambda. Well, what does this mean? It means that the mass function attached to x is given by the Poisson probabilities P of k, or more elaborately, P of k and lambda. On the right of your screen, you see now a visualization of the distribution for the case lambda is equal to 5.3. Again, we notice the unimodal character and that the peak occurs in the immediate vicinity of lambda, in this case at the value k equal to 5, just to the left of lambda equal to 5.3. We see in this picture, again, visible evidence that there is a centering character. And so, appealing to the kind of analysis we did for the binomial, we come up with the idea of a probabilistic center of mass, or more formally, a mathematical expectation for this variable. This is, of course, what more informally we call the mean of this variable, or the expected value, or of course the probabilistic center of mass. But let's stick with the formal terminology. This is the expectation of a Poisson variable. And the intuition here is, as before, imagine a seesaw with weights distributed on it. What we are trying to do is find the fulcrum, the center of mass, where things are in perfect balance. How do we define this? Well, simply enough, we'll call it as before, E of x, the expectation of your Poisson variable x. It is frequently abbreviated by the lowercase Greek letter mu, and it's defined to be a weighted sum. The values that the variable takes, the integers k, weighted by the mass attached to k. Of course, this is a natural extension of the idea of an arithmetic average to a setting where the weights are of different values. Observe that in the expression I've hidden the parameter lambda. So lambda is a fixed parameter which is informing this distribution. Of course, I expect the sum on the right to somehow depend on lambda. So then this is what we're going to attempt to discover. Now, each term on the right-hand side is of the form of an integer k multiplied by a probability P of k. Our first basic Poisson identity immediately tells us how we can resolve this. K times P of k must be lambda times P of k minus 1. And immediately simplifying, we observe that 0 times P of 0 is, of course, 0. 1 times P of 1, with k playing the role of 1, is lambda times P of 1 minus 1. 2 times P of 2, now k is 2, becomes lambda of P of 2 minus 1, and so on down. Every term on the right now contains the fixed parameter lambda, which we factor out of the expression very naturally. And then what remains, we collect inside square brackets, and we realize that what is in the square brackets is a sum of all the Poisson probabilities. But of course, Poisson normalization tells us that the sum must indeed be 1. And therefore, the entire the expression on the right devolves and gives us very simply just the parameter lambda. It's hard to imagine a much simpler expression. The entire excursus here involves just breaking down the probabilities, churning through the Poisson identity, and there you go, Bob's your uncle. You have a simple expression. Of course, when we try to write these down compactly, it's simpler to compact these various terms of the sum into a summation expression. And we could write all these down in a very compact mathematical notation as follows. The expectation of x, that we call mu, is the sum over all k of k times the weights P of k. Replace k times P of k by the Poisson identity, lambda of P of k minus 1. Factor out lambda. The remaining Poisson probabilities add to 1, and we get back lambda. what have we discovered? If x is a chance variable distributed according to a Poisson distribution with a parameter lambda, then the expectation of x is exactly that Poisson parameter lambda. And therefore it is completely permissible and even encouraged to say that we have a Poisson variable with expectation lambda, in place of saying that we have a Poisson variable whose Poisson distribution comes equipped with a parameter lambda. Knowing the expectation tells us everything about the parameter lambda, and therefore implicitly tells us everything about the form of the weight functions, p of k and lambda.